morning, everybody. Welcome to our session today morning. My name is Fabian Born. I'm a technical solution engineer, or solution specialist at NetApp, and I'm still working over 8 years now for NetApp. And today with me, my colleague.
Hi, my name is Hendrik. I'm a solution architect at NetApp, covering everything DevOps, and within that specifically everything around containers and Kubernetes and stateful workloads, storage, data management when it comes to Kubernetes.
Yeah, today we want to talk about non-graceful shutdowns of Kubernetes nodes, which is a relatively new feature in Kubernetes. And before we start to talk about that, we want to clarify some basics like how dynamic storage provisioning works, which PVC access are still existing in Kubernetes, and what is the difference between deployment and stateful set. After the basics, we want to talk about the non-graceful shutdown. And from that, we have some demos prepared, which will Hendrik show you later. And after the demo, we will give you some tips, tricks, handling of a non-graceful shutdown. Okay, let's start with the dynamic storage provisioning in Kubernetes. How it works. So if you want to deploy an application, in our case it's Ubuntu, you need a persistent volume which has to be mounted at /data. For this, we need a persistent volume claim. Every persistent volume claim needs a storage class, which you see in the code snippet. And the storage class itself has a CSI provisioner. The CSI provisioner could be, for example, NetApp Trident or the vSphere CSI. The CSI driver itself provisioned the volume. It creates the volume on a storage controller on the vSphere node and mount or bind this to the persistent volume claim later. After that, let me talk it right. If the volume has been created, the volume will be mounted to the pod, and the application can have access to the volume. Which kind of access mode do we have? So in the classic world, you know some access modes, and it's the same in the Kubernetes world. So we have the read-write-once, which means you can mount a volume read-only to many nodes. We have read-write-many, which can be only mounted to, or can be mounted to several nodes too. You have read-only many, which means you can mount this to many nodes which can be accessed from that. And a new feature, a new mode is the read-write-once pod, which was introduced in Kubernetes 1.22, which means that you can mount your volume only to one single pod. Let's have a look. What are deployment sets or stateful sets? As far in a deployment set, pods are interchangeable. That means you can change the pod from one version to another version, and at the end, the client did not know what pod is running and where is the pod running. In the difference to the stateful set, we need more information. So the stateful set needs a unique network identifier. It needs persistent storage for everything. So if you have one pod, you need one persistent volume for that. If you have more pods, you need more persistent volumes. And all this is, is a big difference from the point. Yes, sorry. Let me check. What is a graceful shutdown now? A graceful shutdown is if you want to reboot a node. So every maintenance activity on your cluster has to be graceful shutdown. This feature is enabled since Kubernetes 1.21. Has to be configured. If you, which kind of configuration do you need? See here. You have to enable the feature gate, graceful node shutdown on the kubelet service, on the cluster management service. You have to configure the shutdown graceful period as a parameter. And the third one is the shutdown grace period critical pods, which is a configuration in the cluster settings. If you did not configure it, these three parameters, every reboot or every shutdown is a non-graceful shutdown. So very important to know for you, if you want to enable a graceful shutdown, you have to configure these three parameters. During the non-graceful shutdown, we have some failure scenarios, and one is the interface failure. What means that? You have an outage on your interface, a switch is damaged, or the interface itself has broken. And what happened with the node? The node is not reachable, but everything on the node is running. The pods are running. The second failure which we identify is the kubelet failure. The kubelet service crashed. The operating system tries to restart the service. And if the kubelet service is not reachable, there's no communication between the kubelet and the master nodes, master one node or the three or more nodes itself. But at the end, the cluster or the pods are running. The third failure scenario is a complete outage of a node, hardware failure, everything else. In this case, the connectivity to the storage backend, to the user front end, has been broken, and nobody can access to this node. In this case, nothing is running on the node again, and Kubernetes is still waiting what's happened with the node. All these three scenarios are failure scenarios, but Kubernetes cannot distinguish which scenario it is. So in this case, you need an external program which have a control plane which connect to the Kubernetes cluster or to the infrastructure platform as a, for example, vSphere to check what's happened with the node. But at the end, Kubernetes did not know what happened now. Let's switch to the demo. To Hendrik, please.
Thanks. Yeah, so let's see how that looks in reality. And before we get to the demo, just a quick look at the setup. We're going to use BusyBox containers simply because we don't really run any useful application in there. We want to concentrate on what happens to the pod and to the volumes attached to that pod. Each of the pods has one volume attached. And in that pod just runs an endless loop that writes the node name of the node where the pod is currently running on, plus a timestamp into a log file. So we can kind of follow what happens on that pod. And we have deployments and stateful sets, two of each. So we have one deployment with a read-write-once volume, one deployment with a read-write-many volume, and you will see later on why. And we have the same for the stateful set, one for read-write-once and one for read-write-many. So there's 4 pods in total, each one just writing the node name that we have. I'll quickly go over the setup, but you can find everything online if you like. So there's the GitHub link here. But we have a volume claim, or actually 4 of those, which looks like this. And there's one for read-write-once and one for read-write-many access mode. We have our deployment. As I said, we have a BusyBox image. We run that endless loop that just prints the node name and the timestamp into /data/log.txt once per second. The node name we get from the pod spec. Kubernetes updates that whenever the pod is rescheduled to another node, so we can easily use that and actually know this is the node on which we are running. And then our volume claim, our PVC, is mounted as /data. So /data/log.txt, that is going to persist everything we write into that log.txt file. Same for the stateful set, except that it has a service because that's mandatory. It's a headless service. We don't care because we don't really run any useful application on there. Otherwise, the container is exactly the same. And then we have a volume template, because that's how a stateful set works. So you can have multiple replicas. We don't. We just use one replica in this case. But if you have multiple replicas, each replica will have its own volume. That's why you have a volume template. Based on that, the volume would be created. But that's kind of our setup. And then the environment is, we have our nodes. We have 3 nodes, 1 master, 2 worker, pretty small, but that's enough for what we need for this demo. We have our pods up and running, 2 deployments, 2 stateful sets. They all run on worker node number 1, which is convenient because it allows us to fail that node and then see what happens, right? And we have our 4 volumes, right? In this case, deployed on NFS and on iSCSI, just because we want to use open standard protocols. Now, what we can also do, if it allows me to start the video, there we go. We can take a look inside those pods. So I'm doing a kubectl exec into one of those pods, and we take a look at that log.txt file. And when we do that, let me pause here for a second. You see that we're writing once per second. We are running on worker node number 1, and once per second we write that into the log file. So that's our setup. And then what we do here now is at the top, I'm going to do my work. In the middle, we have a watch on the nodes because we want to see what happens to those nodes. And right now, all of them are ready. Everything is fine. And at the bottom, we have a watch on our pods because we also want to see what's going on with the pods. And they are up and running. And then we add a timer because I'll fast forward a little bit in here. That's one of the reasons we did a recorded demo, because some of those things take a little while. What I'm doing now is I'll stop the kubelet process on worker node number 1. So we simulate a failure of the kubelet process, but the node is still up and running. And we fast forward a little bit because it takes a while until something happens. And up to about this point here, let me pause there. It's about 33, 34 seconds, and then Kubernetes noticed the node is not ready. So we keep that in mind. I'll cover that in a moment, but it took 30-something seconds until Kubernetes noticed the node is not ready. Our pods are still up and running. At least that's what Kubernetes tells us. It doesn't actually know because it lost the connection to the worker node, so it doesn't know what's going on there. But yeah, they're still up and running because we only shut down kubelet, so all our containers keep running on that node, right? Nothing happens to them. But Kubernetes doesn't know. And then we'll fast forward a little bit more, actually quite a bit, because for a long time, nothing actually happens. It still says everything's up and running, but it doesn't actually know. Up to about this point, 5 minutes something. So an additional 5 minutes from Kubernetes noticing the node is not ready. And now we see our pods go into terminating. So all the pods on the node where we shut down kubelet go into terminating. And then it goes into container creating on at least some of those pods. And before we take a look at what's going on there, I'll explain you why it took that long. Oops, nope, not there. Give me a second. There. So what happens is we have our worker node that has our 4 pods, that has our kubelet. The kubelet process posts a status update to the API server on the master node. And it does that on node status update frequency, which is a value you can configure on the kubelet. By default, that is 10 seconds. So every 10 seconds, the kubelet process tells the API server, I'm good, right? It checks its own status, which might take a little while, right? And then it posts that to the API server. API server persists that into etcd. In case that fails, it has a retry, node status update retry, which is hard-coded to 5 attempts. So if there's like a network outage or something, it will retry 5 more times. In addition to that, there's a controller manager component on the master node. And that goes to the API server and checks if the node status has been updated or not. And that happens on node monitor period, which is another value you can configure on the controller manager. By default, that's 5 seconds. That happens internally to the master node, so it can do that quite frequently, right? There's little overhead. The actual status update from the worker node, it has to check its status, it has to go across the wire, so that is only at 10 seconds, right? And as long as that's fine, everything is good. If the controller manager notices the node status has not been updated correctly, there's a node monitor grace period of, by default, 40 seconds. So it waits up to 40 seconds until it says the node is down, the node is not ready. Now we just saw it was about 33, 34 seconds. Why is that? Well, quite simple. Those are asynchronous processes. So whatever kubelet does here is not aligned with what controller manager does. So depending on how those two align, where you are in that 40 seconds period compared to where kubelet updates the status, it might be a few seconds less. But it's around 40 seconds that it takes for Kubernetes to notice the node is not available. Once it notices that, the controller manager marks the node as unhealthy. And that's what we saw. And that starts another timer, which is the pod eviction timeout. By default, 5 minutes. And again, a value you can configure on the controller manager. But that's why it took another 5 minutes to actually terminate those pods and try to reschedule them to another node. So in general, you can assume that if you run on default values, it takes 5 minutes, 40 seconds for your pods to actually fail over to another node, or to at least attempt to fail over to another node. You can tune all of those settings. Just before you do that, check the documentation because there's dependencies between them. So for example, the grace period should be a multiple of the monitor period, which kind of makes sense, but yeah, check documentation before you make any changes to those values. Now let's take a look at our status. So our node is not ready. We see that we have our deployment container and the one for read write once. Come on. There you go. The one for read write once is in container creating. The old one is terminating, the new one is in container creating. We didn't wait much longer, but I can tell you this is stuck at container creating. It won't come up, right? So we take a look at that, why that is. If we go on, you see that the one for the deployment with the read write many volume, that is actually running. So it's the same deployment, it's exactly the same, just that the access mode of the volume is different, and that actually makes a difference in the behavior, which might be unexpected if you never looked into this topic. But the access mode actually makes a difference in behavior. With read write many, it comes up and is running. With read write once, it's still stuck in container creating, which actually is good, but we'll discuss that in a moment. And then we have our stateful set, and that stateful set is stuck in terminating, but it doesn't even try to reschedule that to somewhere else. So what's going on? And I'll start with the deployment with the read write many volume. It's a deployment, so Kubernetes has no guarantee on the pod being unique or there being only one pod. No at most one semantic here. So Kubernetes says, okay, the pod is terminating. I don't actually know if it even is terminating because I cannot talk to the node anymore, but I don't care, I just bring up a new one. That's why you see it goes into container creating, right? And then we have a volume, and the volume is read write many. So the property of the volume is, yeah, you can attach that to multiple nodes at the same time. So the deployment is not blocking creating a new container. The volume is not blocking being mounted again, even though it is still attached to the original node. And that's why that comes up and goes into running state, which is not good. And we'll take a look at why that is. There you go. So I'm going to, again, take a look at the log file we're writing on that read write many deployment. And what you see now is that we have 2 entries per second, one from worker node number 1, one from worker node number 2, because the original container is still running. It's still writing to that volume. But Kubernetes also started the container on the other node, which also has the volume attached because it is read write many. So they are both writing to the same file. If your application is not built for this, this is the point where you have data corruption. Two processes running to this, writing to the same file. You might have some file system locking mechanisms. You might have, some SCSI blocking in there, but there's no guarantee, right? At this point, you could have data corruption. So that's not good, right? But that's kind of what you get from this. If you look at the read-write once deployment, same deployment, just a different access mode. Again, the deployment tries to bring up a new pod because it doesn't have any guarantee on a deployment, right? It doesn't care if the old one is still running or not. But the volume is read-write once. So Kubernetes knows I should only attach this to a single node. And it actually keeps track of those volume attachments. So that's why it doesn't attach the volume to the new node, and that's why the container is stuck in container creating. The container tries to come up, but it can't because it doesn't have access to the volume. We can take a look at that as well. So I'm doing a describe on that pod. And from that describe, we see Kubernetes gives us a multi-attach error for the volume because that volume is already in use by another pod on another node. So it keeps track of the attachment and says, I cannot bring up the container because the volume is still in use. And we can actually see those attachments as well if you do a kubectl. There it is. If you do a kubectl get volume attachment, you see all of those attachments. And I'll stop there for a moment. You see all of them are still on worker node number 1, except for the read-write many volume. That is now on 2 nodes because it's been attached to both. So that's why we have 5 attachments here, 1 on worker node 2. Everything else is still attached to worker node number 1. Kubernetes keeps track of that. And then we have our stateful set. And those were not rescheduled at all, right? They're stuck in terminating. And that is actually a property of a stateful set, right? A stateful set guarantees there's at most 1 pod running. So as long as the one is still terminating, Kubernetes will not even try to bring up another pod. That's the good thing about a stateful set. It's built for stateful workloads, so it protects us from those data corruption issues, right? It doesn't even try to bring up a new pod if the old one is still somewhere, right? But maybe we want to have our application back online, right? So what do we do, right? What do we do to clean up all those pods that are stuck in terminating? Anyone thinks force delete is a good idea? Yeah, sure. Let's try it, right? Let's give it a try. What could go wrong? So what I'm doing here is I'm force deleting all of those terminating pods. And that gives us a little warning, but it's okay, right? And we fast forward again a little bit because this takes some time. After about 50 seconds, we see the stateful set read-write many is now in running state. And that is simply because we terminated the pod, so the stateful set thinks there's no more pod. It's still up and running, but the stateful set now believes it doesn't exist anymore, so it can bring up the new one. The volume, again, is read-write many, so the attachment is not blocking us, and that's why this is now coming up. The 50 seconds is just random stuff, random time it took to bring that up, right? But in this case, now we actually have, and we can take a look at that, the same data corruption issue on that read-write many stateful set as well. So if you take a look at that, you will see that we now have 2 entries per second, 1 from worker node 1, 1 from worker node 2, even for a stateful set. That's what we triggered by the force delete. And then we'll fast forward again because nothing's happening up to about 6 minutes. And then we see that even our read-write once deployment goes into running state, so that's now working. And a few seconds later, and that's just, again, stuff it, random time it takes to bring that online, then the read-write once stateful set also goes into running state. So now everything failed over to the second node. It took 6 minutes, right? Plus the time to bring up the pod. Why 6 minutes? Well, another wonderful timer in Kubernetes. There's a max wait for unmount duration timer, which is actually hard-coded to 6 minutes. So you cannot change that. It's hard-coded in the attach-detach controller of Kubernetes. Whenever a volume attachment is not cleaned up within 6 minutes, Kubernetes assumes it is safe to attach that volume to another node, which it might not actually be, but Kubernetes makes that assumption. So we force deleted the pod. The force deletion of the pod triggers a force deletion of the volume attachment as well because there's a dependency between the two. So the volume attachment is gone. Kubernetes waits for the CSI driver to report it has actually been unmounted, but it only waits 6 minutes. And after that, it says, okay, I'll assume it is unmounted. I just mount it to another node. Before Kubernetes 1.24, it would actually do that on a healthy node as well. So if there was any issue in your CSI driver, any issue on your storage solution where it would take more than 6 minutes to unmount something, it would just remount that to another node after 6 minutes, even though the node was healthy. That is kind of risky, so that's why it was changed in 1.24. And it now only does that on nodes that are not ready. But on nodes that are not ready, if we force delete the pod or force delete the volume attachment, after 6 minutes, Kubernetes will just remount that to somewhere else, which again brings a potential issue of data corruption. So how do we handle that? And there's one important thing here. Whatever you do, make sure that this node is actually down. Because as you saw, the containers just stay up and running. They just continue writing to that volume. And the only way to prevent that is to actually shut down the node. Right? Physically shut it down if it's bare metal, shut down a VM, whatever you have. Right? Make sure it's shut down. Make sure it doesn't come back online in an uncontrolled way. Like if you had a network outage and then networking comes back and the node will just keep writing to that volume. No, you don't want that, right? As long as your application cannot handle it. If you have your own logic in the application and it works with replicas and its own leader election, all those kind of things, then it's fine. Your application can handle it. But there's applications out there who can't, right? From that point on, there's a number of options. You could delete the node. You only do that if you don't want to recover it, right? Because it's gone from the cluster. But deleting the node is an easy way to move everything off that node. If you delete the node, Kubernetes will move all the pods, all the volume attachments, everything to the other nodes in the cluster. You don't have to do it one by one on each pod. Some of the managed Kubernetes solutions out there actually try to do something like that automatically. So they have self-recovery, self-healing processes. So you might experience that in your Kubernetes distribution if it does that. The other option you have is new in Kubernetes 1.24, and that is the non-graceful node shutdown feature. And as Fabian explained earlier, if you don't enable graceful shutdown, everything you do to a node automatically is a non-graceful shutdown. It is still an alpha, so you need to enable a feature gate to get that. So you enable the feature gate, and once you have that, what you can do is you can put an out-of-service taint on that node. That's a manual process, but it's a way for you to tell Kubernetes, I ensured the node is shut down, it doesn't do anything. I maybe want to recover it, but please move all the workloads over to another node. Right? That is what this taint does. And yes, it is a manual process. You need to manually make sure the node is down and then manually apply that taint to the node. That is the first step, right? After that, there are plans to automate this within Kubernetes. This is the first step to at least get a mechanism to tell Kubernetes it is out of service, right? Previously, we didn't have that. So that's new in 1.24. And then there's ways you could do node fencing. And there's a couple solutions out there. All of them are not really well maintained. The one I'm listing here, kube fencing, seems to be the most well maintained out of all those not very well maintained. But that's essentially the classic shoot the other node on the hand approach, right? You have an application running on the healthy nodes that figures out the node is not ready anymore, and then it kills that node. And it does that by using out-of-band management capabilities. So IPMI on a physical server, some baseband controller on the physical server, a connection to your VMware to shut down the VM, a connection to your cloud provider to shut down a compute instance, those kind of things, right? And that actually automatically makes sure the node is down, so you don't have to do it manually. And then after that, it can also evict all the pods from that node if you want. And also, there's some CSI drivers out there who try to protect you from that data corruption issue by doing some I/O fencing on the storage system side. So that exists as well. None of those solutions is really perfect, I would say, but that is kind of what you have available today. So lessons learned, read-write-many can be dangerous, right? Only use it if your application can deal with the fact that multiple instances write to the same file. Otherwise, stay away from that. And that might not be very obvious if you start using PVCs, right? Typically, use a stateful set for stateful workloads. It's built for that, right? And it protects you from those corruption issues compared to a deployment who just brings up a new pod. Be careful with force delete, should be obvious, but just saying it again. And yeah, that automated failover of stateful workloads in Kubernetes is still a bit tricky. There's no perfect solution today, but we're getting there, right? And that's kind of what we had. So any questions?
Cool.
Anything that came in?
Yeah.
No?
Cool.
Yeah.
All right. Yeah. Thanks. Hendrik. You realize that then. Yes, we do have a few questions. Obviously, most of them are with regards to read-write many and read-write once. Can I just use read-write many for everything? Is there any benefit from using read-write once?
Yeah, you can, right? But the downside is Kubernetes then makes the assumption it is safe to attach to multiple nodes. Make sure that is actually true for your environment, for your application, right? In that case, yeah, it actually has benefits because if you do rolling updates of pods or something, that actually is a little easier with read-write many. But make sure your application can handle the fact that multiple instances access the same file potentially.
Cool. Okay. Second one: if kubelet fails, does the service is the service able to forward requests to pods?
I believe yes, because that is not handled by the kubelet process itself. But yeah, it's a matter of what actually fails on that node, and there's a lot more scenarios than what we covered today. But depending on what that is, there might be a gray area, right?
Cool. Why do you have pods with, again, read-write only? Would it be bad to have that pod with read-write only?
I think we had that, yeah.
Shameless plug, watch my on-the-one. Oh, come on. But fair enough. Shameless plug. It provides a shameless plug. Watch my on-the-one session about
I will watch it,
Kubernetes.io, which is about fencing and repetition using operators. Actually, I apologize. Actually, that's quite nice. We're here to share information, and it's not just the speakers, but thanks for that. Why can't he drain the node?
Well, in the scenario we had, you cannot talk to the node anymore, right? The master node cannot reach the kubelet process on the worker node anymore, so it cannot do anything about it. That's the base issue, right?
And final one, if we delete an auth-ready node, does that guarantee that the volumes will actually get unmounted from that node?
They will, but not in a clean way, right? So if you just delete the node, it starts clean. Kubernetes assumes, that is gone, I can do whatever. If you don't shut it down, well, it keeps running, right? So maybe not a good idea. It will fail over, but probably cause other issues.
Don't force delete. All right, cool. Thanks again, Fabian. Thanks, Hendrik.
Any other questions you have, you can find us at the booth, which is a little further down there, the one that has all the 60-node blinking cluster. You really cannot miss it.
Oh, cool.
So
awesome.
Happy to see you there if you have any other questions. Thank you.
Obviously, they're still here for the rest of the day. Do go and see them. Do check out the sponsors. As I said, we couldn't do a conference like this without them. Thank you. See you in 10 minutes.
Thanks.
Thank you very much.